If you're an automotive design engineer that needs some wishes granted so you can fit more functionality into a smaller, lighter, and lower cost design, you need to start sending your wish list to Rick Bravarsky at Infineon Technologies in Michigan, because he's been granting way more wishes for designers than anyone at the North Pole or anywhere else. Rick is with us today to talk about how Infineon is addressing designers' system-level needs in low-voltage automotive motor drive applications. Welcome to Tech Chats, Rick.
Hey, thanks, Chris. Thanks for having me.
Now, when people hear electric motors in cars, they might jump to traction motors for EVs, but the topic today is actually the low-voltage motors. So let's talk about what that means and where those are used.
Sure. So yeah, low voltage, that means we're likely talking about the traditional 12-volt battery and say motors, say below a kilowatt. Because some of the bigger stuff, like compressors and things, are likely moving on to the 48-volt rail, or might be handled differently in an EV. But yeah, as you mentioned, honestly, on the 12-volt side, let's say we're talking about body and comfort systems, there's really no difference between an EV and a standard internal combustion engine vehicle. But in general, yeah, there's typically more than about 35 motors per car today in this category below a kilowatt. So yeah, motors are growing at about 5% a year, average growth rate. And BLDC is growing slightly faster because some motors are actually converting to BLDCs. We have new loads coming in, and at Infineon, we have a lot of products. We look at all these different applications, and we figure out how we're going to address these things. We have a big technology portfolio, many technologies to choose from. So it's a question of applying the right technology and ideally hitting it in, the right combination of integration and features that our customers want to use. Now, we're not going to get to all of them. I mean, it's a huge portfolio. So we'll touch on a few key products, give you a sense of the breadth of our portfolio, and hopefully that will start a conversation later on. So, but as I mentioned, we do look at what are our customers' top system level needs. We know everyone's trying to reduce size, reduce costs, and we support that by further integrating our products, making things always smaller and putting more features into them. Efficiency, so reducing the key off current, but now with EVs, of course, even the operating current becomes very important. How can you get the most range out of that battery? So we've been focused lately on even reducing our operating currents. Customers expect high reliability and robustness. When you look at these smart power devices, as we keep shrinking them to reduce the costs, when there is some kind of a short circuit or a fault condition, you're looking at energy levels that can be higher than the surface of the sun. So as we shrink, we have to have more intelligence in how we handle these fault conditions. If we're talking motor drive, there's always EMC, the emissions, what kind of audible noise are you making and what kind of electrical noise are you putting into the system? And our customers have to design around that and filter it out and get rid of it. So we'd like to give people as many tools as possible to make that job as easy as possible. And it's some programmability in these smart devices. And lastly, we look at scalability. We know our customers are trying to do a lot more with less these days. I mean, the one resource that's completely finite is time. So we try to even design our products with scalability in mind, create families that our customers can easily switch from member to member, and ideally reduce their software development, which is now probably the single most expensive part of the development process is the software itself.
Now, you mentioned you have a bunch of different technologies in your portfolio. So how are you using that portfolio to address these system level needs?
When you look at, say, the basic motor drive block diagram, there's always the same pieces are there. You got to have a brain, the microcontroller. You got to have the power side of it, the thing that's driving the motor. So typically MOSFETs, some kind of gate drive, something that controls those power drivers. Communication to the outside world. So all these pieces are really the same, no matter what block diagram you look at. And then sometimes even on board, but more typically off board, there might even be a sensor that's bringing information into the vehicle. Infineon makes all of these pieces. And again, we may not get to all of them today, but you'll get a good sense of how much coverage we do have here. By having a lot of different technologies, we have a few different approaches. It's not just, well, here's our motor driver, I hope you like it. But we have a lot of different ways to drive motors. So we have, say for brushed DC, we can be disintegrated at different levels. And then the same thing for brushless DC. But we also have at the other extreme is very high integration. So a system on chip product, like we call our embedded power device, which is pretty much everything but the MOSFETs in one chip.
And within that range of possibilities, what are we looking at today?
Let me highlight one of our simpler devices here, what we call the Novalithic. So when you're looking at the block diagram, it's combining the MOSFETs, both the high side and low side MOSFETs, so a half bridge with a half bridge driver and some other intelligence into one package. Our next generation coming out will be in this tiny 7 by 8 millimeter leadless package. And our previous generations, we've delivered over 500 million of these parts already. They're very quite popular, these monolithics. And if you look at them in a circuit, let's say you're doing a half bridge, one of the reasons why they're so popular is they're very simple, very easy to use. It's one package. Again, you've got, it's like a system in package. You've got the two MOSFETs and the driver IC. And with just two digital I/O and one analog pin, you're driving a half bridge. So you've got just a real simple inhibit or enable pin to wake up the device or put it back to sleep. The input pin changes the direction. You turn on one MOSFET or the other one. And then you've got, of course, the current sense coming back, some kind of a fault flag, and some other information as well. You can put two of these together and make an H-bridge very, very easily. So on either side of the motor, and now by turning on one high side and then the opposite low side, you're spinning the motor in one direction. Flip that around, you're spinning the motor in the other direction. And this now it's only 4 digital I/O, and you can even take those 2 analog signals and share them on the same pin. So get it down to 5 pins. Very simple software, very easy to use these. Part of what makes them very easy to use is that there's a lot of protections built into them. But before I move on to that, I've shown you half bridge, I've shown you H bridge. There are customers who even use 3 of these and create brushless DC solutions as well. So very, very simple. But inside of this, why our customers like this device is they often describe it as having a belt and suspenders protection. When you have external MOSFETs, the MOSFETs are kind of on their own there. There's certain kinds of short circuit detection you can do, but what you can't do when the MOSFETs are external is temperature protection. And often, when your gate driver is separated from the MOSFETs, you're really reliant often on the microcontroller to come in and make decisions. With a monolithic, because the protections are built in, this will run independently from the microcontroller. The protections will, so you're still protected even if the microcontroller goes out into the weeds. So it's got built-in cross-current protection. You cannot turn on the high side at the same time as the low side, so you won't get that shoot-through short circuit. There's overcurrent detection and protection on both the high side and the low side. There is a temperature sensor built in into the top chip, and so it monitors the temperature directly. And then all this information can be fed to the microcontroller. We have our IS pin, our current sense pin, but it's more than just current sense. The fault flag is there, which is distinguishable from the current sense. And with the new devices coming out, you can also get a direct temperature reading. So you can actually read directly the temperature of the device. But the device itself is, again, self-temperature protected. So the monolithic is pretty unique in that it's the size of it, again, this feature set, we've seen people try to imitate it, but they've never been successful. And it comes down to this very unique construction in that we have these 3 chips in one package, but it's chip-by-chip construction and a chip-on-chip construction. As I mentioned, we actually put the top chip right on top of the PFET, the high-side switch. So we're fitting 3 chips in as small of a spot as possible. And okay, it's a simple idea. You see people come after this device, but no one's been able to make a real direct copy of it just yet. And that's part of the trick there. So like I said, we shipped over 500 million of these. Today, there's our BTN8962 or BTN8982. You'll find them on our website, very, very popular devices. And then our next generation is coming out very, very shortly. Already sampling it. So that's our monolithic. That's one of our simpler devices.
So if that's one of the simpler devices, then what do we get with something a bit more complex?
So the next step is let's look at a different kind of integration, what we call our MultiMOSFET Driver IC. So coming back to the block diagram of a typical motor drive application. In this case, a different kind of integration. Now we're taking the gate drivers, multiple gate drivers, and putting them all into one package. And this is great for multi-motor applications. Like I mentioned earlier, seat modules. There's a lot of motors in that seat module. Often power lift gates might have more than one motor. You might have either the door is big enough, there's a motor on each side, there can be the wiper, there can be the washer, there can be other things, the latch motors itself. So there are now applications where you're driving multiple motors from one place. So having multiple gate drivers in one chip is a good way to go depending on the power range. So looking at it in the circuit, you got a microcontroller, again, the power supply, and this device, again, that drives all the MOSFETs. So we have one device that's designed for doing 2 motors completely independently. So it's 4 half bridges. So you can have 2 H bridges. And if your application allows cascading, allowing motors to share the half bridges, to share the legs, you could even do a third motor as well. It just means you can't necessarily run all the motors at the same time. And it even has an extra charge pump to actually drive a reverse battery MOSFET. And there's other flavors of this device. There's another one, what we call the eightfold device that can drive 8 half bridges. So again, if you allow, 8 half bridges is 4 motors with independent control, or up to 7 motors if you allow cascading. So a couple different flavors of this device. You can then scale up and down. I want to highlight a couple key features of this device. We have built-in op amps. So current sense op amps are built into the device. And there are other gate drivers that have built-in op amps. But what we did with this one, since the op amp is there, we're actually reading it. We're looking at the current that's going through it. So our device can make some decisions on its own and offload the microcontroller. So in particular, almost every gate driver I've seen has some kind of short circuit protection, and it's what I would call hard short circuit protection. It's easy to recognize when there is a hard short circuit. What's tricky to do is, what is a soft short? Something between normal operation and not a very obvious hard short circuit. How do you recognize that? And so maybe you're doing some current sensing and letting the microcontroller make some decisions. Because we're right there, because we have the op amps, we can actually read them very, very quickly. In as fast as 6 microseconds, we can make that decision and offload the microcontroller. So rather than waiting for the microcontroller to take the read, make the decision, send back the commands, which can be, some milliseconds, we can respond in microseconds and recognize a soft short circuit based upon thresholds and timing set by the user. And we can make that very fast decision. And customers have found that this enables them to use smaller MOSFETs, higher RDS(on) MOSFETs than they might use otherwise, because we react so quickly, the MOSFETs are better protected. So another key feature of the MN gate driver is what we call adaptive MOSFET control. So really the status quo today is that gate driver devices, you can tweak your slew rate, you can change the current, but it's a constant current. So maybe you're taking a pull down resistor and using that to tune what is the gate current going to the MOSFET, or maybe it's a setting in an SPI register. It's like one of 4 choices. So you're making a compromise. So either it's trial and error with external components, and you're locked into one choice, or with SPI you've got 4 choices. But what if you need a choice right between these two? Well, too bad, you only have 4 choices. So with adaptive MOSFET control, what we've done is we now have multi-stage current control. And if you're looking at this animation on the screen, you can see in the green there, that's the gate charge. And you can see there are multiple phases. There's a peak on the left, we call the pre-charge. Then there's a nice plateau, and that's the slew rate. That's the danger, the EMC area. And then when we get out of that zone where EMC is an issue, then we have the post-charge. And we actually have, I would say, some nice levers and knobs that you can turn through software to tune these things. And what the pre and the post-charge do is they actually help you reduce your power dissipation. Because if you're on the left-hand side, you're talking about that's the dead time where you could be in recirculation mode and there's current going through body diodes and there's a lot of heat. And then on the right-hand side, once you get out of the EMC zone, you're still not fully enhanced. You can see it in the blue trace, is that the current is still not flowing completely, and that means the RDS(on) is not as low as it could be. So when we're out of the EMC danger zone, we hit the gate as hard as we can to get to that low RDS(on) as fast as possible. So we're saving power dissipation. And then, of course, you can always, tune the slew rate. And so what you see here, you can actually see in the pink, that's actually the slew rate. You can see that that's moving and changing shape. Now, stepping forward to a different view, we can also keep the slew rate fixed, and we can then move the dead time back and forth. So really a lot of control here that you can't get out of other gate drivers. If you just have constant current, you're not going to get this level of control. So again, the benefit is you can tune your EMC. Yeah, it's some trial and error, of course, it always is, but it's not fixed in hardware. It's not taking up board space. And you can tune this on the fly. It makes your development process go much, much faster. And in the real world, actually, you could then have multiple profiles in your software. And maybe under this condition, I want this profile. Under these conditions, I want that profile. So very, very flexible. But really the key message is helping the customer do their EMC development, pass their testing as fast as possible. Another key feature of this device is what we call our brake mode and generator mode. So, all right, these are actually somewhat standard features today. But the key here is we've actually designed brake mode and generator mode that will work while the module is asleep. So that's the trick. And in both of these cases, not only are we, detecting the generator mode, we're also detecting if there are faults happening. So we're doing a lot now in sleep mode, still keeping very, very low quiescent current while providing some critical functions. So rounding out this family, like I mentioned, there's a couple different flavors of it. 8 half bridges, 4 half bridges. They come in the same package. They can use the same software. So very, very scalable, keeping the designer in mind as we design our products. So now moving to another level of integration, taking everything, taking the MN driver, the MultiMOSFET Driver IC, we now add to it some of the other support pieces, the power supply, the communication interface. So the MN Driver IC has actually been very, very successful. We're getting into all the target applications. It's rolling out the last couple of years quite nicely. And then typically this device tends to be paired with one of our system basis chips. We call it SBC. These two devices, the TLE92104, 92108, tends to be paired up with what we call our mid-range plus SBC, the TLE926X, typically the 9262. This combination of devices is in all kinds of comfort motor drive applications around the world. So what we've done, always looking to further integration, is we've taken sort of the greatest hits of these devices and put them now into one device, what we call the motor system IC. So it's gluing the gate drivers and the SBC together into one package. So all kinds of features rolled into there, and the fail-safe modes that we get from our SBCs, and of course we kept the charge pump for driving the reverse battery MOSFET or another kind of a safety switch. So again, really the greatest hits of these two devices wound down into one tiny little 7x7 package. And this is again a family, very, very scalable. So we've got a half bridge variant. We've got a few different variants driving 4 half bridges, so it could be 2 DC motors, and we also have some brushless DC variants as well. But now let's roll up one more level of integration. Let's go even to a higher level. So say going back to the block diagram, now we're rolling up everything but the MOSFETs, so what we call our embedded power ICs. So now we've got the microcontroller, the bridge drivers, we've got the power supply, the communication, all of that rolled into one package, and then it's just a question of sizing the MOSFETs around it. And embedded power, it's a pretty complicated family. I mean, once you throw a microcontroller into there, anything becomes complicated. But it's a family of devices, a family of families, in fact. We have relay driver devices. We got some that just have a half bridge drivers, some for doing H-bridge and some for doing BLDC three-phase driving. And any one of these is its own subfamily with multiple flavors, scalable by memory size and some other features. And we're now at least our third, going towards our 4th generation of embedded power devices. And because everything is now integrated into one device, there are things you can do with embedded power that you simply cannot do with a discrete approach. So let me highlight one of these and also, dispel one of the quick misperceptions about this device. Someone glances at the data sheet, they might say, boy, I only see 8 A to D ports, and I don't think that's going to be enough for me. But what may not be obvious is that there is, in fact, a second A to D. This is a 10-fold, 8-bit A to D internal to the device. It's already pre-wired to handle all the typical protections, internal temperature monitoring, all kinds of different voltage monitors. It actually monitors the reference voltage of the other A to D. And so in the end, it leaves the general purpose A to D free for whatever else the customer wants to do. But all of the things that we think they want to do are actually already pre-wired and already set up in there. And there's a lot of programmability, adjustable over voltage and under voltage detection. The overcurrent detection and shutdown features, adjust the threshold, adjust the timing. There's a lot that can be done in the off state. You can monitor for failures of these MOSFETs while still remaining in the off state. In other words, you don't need to actually activate the motor or try to turn the motor to do the full diagnostics. And I guess I should mention also it's an ARM core microcontroller. Depending on which flavor of device you're looking at, it could be the M0 core, or for the more complicated BLDC types, it's the M3 core. And our roadmap is still expanding on this family as well. So that's embedded power in a nutshell. Again, keeping in mind that almost everything else I've talked about also rolls up into the embedded power device. I mentioned we've got all the pieces here at Infineon. So that includes also the MOSFETs. I can't forget those, the sensors, and the microcontroller. So in the microcontroller world, if you do want a standalone microcontroller, we have the Treveo 2 series, what we call really the body series. Is typically what's going to pair off in these motor drive applications. So we've got microcontrollers, and then also the MOSFETs. We have a lot of MOSFETs. Speaking of scalability and broad portfolio, we make a lot of MOSFETs. But I do want to highlight one new package type that we have that's unique to Infineon. So many people have dual MOSFETs, two MOSFETs in one package. But the existing packages actually create routing issues. You're running traces all the way around the device, so you end up with some longer traces, and those longer traces create inductivities. So stray inductances, and then they can create voltage spikes that will require some kind of filtering. So we have a new family coming out we're calling the half-bridge configured MOSFET. So we've wired it internally, already in a half-bridge configuration, which saves a lot on the external traces, and then it also saves on that filtering, maybe even removes it entirely. So it's a different option from Infineon, saving board space and saving external component costs. So to recap, I said we have a lot of different ways to skin the cat here, whether it be brush DC motor drivers, whether it be BLDC motor drivers, whether you're looking for fully integrated solutions or discrete. We've got the big portfolio. We cover a lot of different options. And we always are keeping in mind, what do our customers need? We try to provide what our customers need through our integration, our efficiency, intelligence, programmability, and scalability. So, put it on your wish list. Let us know what you're looking for, because we want to make products you want to buy.
Awesome. And thanks so much, Rick. Once again, that's Rick Bravarsky from Infineon Technologies. If you'd like to learn more about Infineon's automotive low-voltage motor drive solutions, click the links in the description or visit Mouser.com. And be sure to check back soon for the next episode of Tech Chats.